Hello everybody, welcome to another wonderful day here of multivariable calculus, also known as Calc 3. We're going to learn today about the dot product and the consequences of it and all that fun stuff. So the dot product is when we can dot two vectors. We don't multiply two vectors, we dot them. It's just a different operation. And all that means is we take each component of the vectors and multiply them, and then we find the sum of all of those products. That's it. So if you have v dot w, and I just show you 3-dimension here. Obviously for 2-dimension, you're just adding two terms together. If we went 4-dimension here, you'd be adding up those four products. And this is going to give us a scalar value. So when we do v dot w, we end up with a scalar value, which is just a number. So I get asked this question all the time. What does a dot product actually give us? It actually gives us the length of the projection of v onto the vector w. When those two vectors are placed and their tails coincide. So that really doesn't mean much to anybody, but what that really does mean is that if we have v dot w, it's the same thing as taking the magnitudes of v and w and multiplying them times the cosine of the angle between them. So within that, we do have some properties here, and we'll show you some of these properties as we go through. The most consequential one probably here is the v dot v is the same thing as the length squared. So v dot w is w dot v. Everything else here, if we do have the zero vector dot any vector, you're going to end up with a 0. So there's some more geometrical properties. We'll get to those part in just a second. Let's go ahead and go through example 1 right here. We have u is 2, -3. We have v is 4, 1. Let's go ahead and do u dot v here. So when we do u dot v, that's just going to equal 2 times 4. So 2 times 4 plus -3 times 1. So we're going to get 8 minus 3, which is 5. Okay, so we get a value of 5. It's just a scalar value. What that means is if I found these two lengths right here, and I multiplied them, and I knew what the theta value was of the angle between these two vectors, then those would equal. So we'll get to more application just a bit of the dot product to maybe put a little more understanding to it. Let's go ahead and go to this next one. Let's go ahead and find the magnitude squared. So let's find the length of v. The length of v here is going to be the square root of each component squared. So it's 4 squared plus 1 squared, which is going to be root 17. So if I were to find that magnitude squared, that would be root 17 squared, which is just 17. Now I could have done this another way by doing v dot v, which would be 4 times 4 plus 1 times 1, which is also 17. Okay. Now let's get a bit of a geometric understanding of what's going on here. And let's go ahead and look at this box right here about the angle between two vectors. If theta is the angle between the two non-zero vectors, u and v, we'll just pick theta between 0 and pi. We never really pick it between pi and 2 pi, but that doesn't make much sense for us. We're just trying to find the closest angle between them. Then cosine of theta is equal to u dot v over magnitude of u times magnitude of v, which is really a direct consequence of solving for cosine theta up here. And also the geometric term orthogonal. So two vectors are orthogonal if the vectors u dot v is equal to 0. So that's orthogonal. Okay, so let's go ahead and show why this even works. When we look at example 2 here, we're going to prove that the cosine theta equals this formula is true. So cosine theta equals u dot v over length of u times length of v using law of cosines. Now in AP Pre-Calc, you may or may not have gone over that law of cosines. So what I'm going to do is I'm going to just draw a picture here and show you what law of cosines is. So law of cosines says that c squared is equal to a squared plus b squared. Sounds kind of familiar, but we're going to subtract 2ab cosine theta. So that's the law of cosine. So what I'm going to do is I'm going to just take this red triangle right here and kind of put it up here to be these vectors. So that you can see this picture has two vectors just randomly. It's u and v, and this resultant right here is just v minus u. So we're going here, and then we're going in the direction of u, and that resultant is going to give us, the opposite direction of u. This right here is going to give us v minus u. Okay, so I'm going to label this as A, this is B, and this is C. So I'm going to kind of replace everything from here and put it over here. Now I'm dealing with lengths. So A should be a length, so it's going to be the length of u. B should be a length of v. And C is going to be a length of v minus u. So let's go ahead and do that. So the length v minus u is equal to u squared. Oh, that should be squared, by the way. So length of C squared equals length of A squared plus, you can see this magnitude over here, magnitude of V squared minus 2 length of U, length of V, cosine theta. Okay, so what I'm really going to do is just kind of play around with this one over here, and then I'm going to put everything all back together here. So I'll do this in blue. V dot U squared is the same thing as V minus U, or V, sorry. Length of V minus U squared, same thing as V minus U dot V minus U, if you remember that from our previous slide. And then so I'm going to do V dot V, so V dot V minus V dot U minus V dot U, and since those are, order does not matter, I can write that as minus 2 UV dot, 2U dot V plus U dot U. And if we can recall, V dot V again is going to be length squared minus 2 U dot V plus U squared. So what I'm going to do is I'm going to do a substitution here of this blue. So I'm going to get V squared minus 2U dot V plus U squared. And that's going to equal the rest that I have over here on the red side. And hopefully you see what's happening here. Should be length. So what's happening here is we do have these v squareds will end up canceling out. I'll do that in purple. So those lengths of v squareds are canceling out. I can already see I forgot to put. Not very meticulous. I apologize. There we go. So these will cancel out. These will cancel out too. And we're left with negative 2 UV U dot V equals negative 2 U times V cosine of theta, and it'll just divide this negative 2 length of UV on the other side, and you'll end up with the negative 2's canceling out, U dot V all over these lengths. You can put a times sign if you want between those. Since this is there two scalars being multiplied against up with the dot, that does not mean dot as in vector dot. It's just multiplication. All right, squeeze it on in there, and there you go. There's your proof of the law of cosines. So with this information here, let's go ahead and find that angle between vector v and, oh, I see a little typo here. It should be a vector w. It's not labeled as vector. So I'm going to do that. So you can see that. Hey, look at that. It's a vector. So I'm going to find the angle between those. So I'm going to first do v dot w in this case. I'm going to do 2 times negative 1 plus negative 1 times 1 plus 1 times 0, which is going to give me an answer of negative 3. Yeah. Length of v is going to be 2 squared plus negative 1 squared plus 1 squared, which is going to be 3. Yeah, 4, actually no, root 6. Ugh. Sorry, I'm not that good at arithmetic. Root 6. And then for, oh, this should be w. Vector w, this length, end up being 2. Negative 1 squared plus 1 squared plus 0 squared is root 2. So we do know that cosine theta is equal to 3 over root 6 times root 2, which is root 12. Root 12 is, I'm going to rationalize it here just so I can make this look like a nice unit circle value, because I believe this is unit circle value. This is going to be 3 over 2 root 3. Yeah, and if I multiply top and bottom and rationalize it by root 3, I'm going to end up with root 3 over 2. Yeah. Oh, and this is a negative. I didn't notice that. This is a negative, so that's negative, 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 so negative. So when does cosine of theta, that's poorly written, I apologize. When does cosine of theta equal negative root 3 over 2? That's going to happen at, you got to be sharp at your trig here, 5 pi over 6. Quadrant 2. Yeah, 5 pi over 6. Let's go to the next problem here. It uses the terminology orthogonal here. Find the scalar a so that v and w are orthogonal. Orthogonal means that the dot products are equal to 0. And by the way, if the dot products are equal to 0, so if I have v dot w and that equals 0, that means that cosine of theta is equal to 0. When does that happen? Happens at pi over 2, or 90 degrees. So if they're orthogonal, then these vectors are perpendicular. I think I put that up here. I did not put that up there. So there you go. So orthogonal means perpendicular. Okay, so let's go ahead and do v dot u. So when I do v, or w in this case, v dot w, I'm going to get 2a minus a minus 1, and that needs to equal 0. It's going to be a minus 1 equals 0, so a is going to equal 1. That is when the value that we have where v and w are orthogonal, so they produce a right angle. That's my best right angle I can make, I guess. Just more consequences on this dot product. We actually have a lot of notes going on here. We have direction cosines. So direction cosines, you can see this picture right here. We're going to go direction from any vector v. This is in 3 space, by the way. You're going to have the alpha angle be the angle to v along the x-axis, or the I vector. The beta is going to come from the j, which is the y, and the gamma is going to come from the k, which is the z-axis right here. So this vector, which again, this end is right here. Okay, you're just looking at all those little spaces in between there. So we can rewrite any vector as directional cosines. So you can find each cosine, by the way, by doing this right here, by taking each component and finding the unit vector, really, of each if you find the unit vector within each component, and then we can rewrite it as this right here. So let's go ahead and do that. So find the magnitude and the direction cosines of this vector right here, and then we're going to write v in terms of its magnitude and direction cosines. So all that means is we need to find the magnitude, and then we can rewrite all of these cosines as this, and then we can rewrite our vector as this v down here. So let's go ahead and find the magnitude of v. Square root of negative 3 squared. So we're just taking each component and squaring it. This is going to give me, what, 9 plus square root of 9 plus 4 plus 36, which is root 49. That's pretty nice. So 7 is what I'm going to get here. So I can rewrite this as cosine of alpha. To find the alpha value, that's going to be, the component is negative 3, so negative 3 over 7. To find cosine of beta, that's going to be 2 over 7. And to find the cosine of gamma here, we're going to get negative 6 over 7. So those are the directional cosines. These are not pretty numbers, which are the unit circle. So I really can't solve for these without a calculator. I can't figure out what all of these angle values are. But I can write this v as these directional cosines. So I'm going to do 7 times, and then I'm going to take cosine of alpha of this. So it's just going to be negative 3/7 I, plus cosine beta, which is plus 2/7 j, and then plus cosine gamma, which was negative 6. So actually, I'll make that a minus sign. So minus 6/7. Okay. All right. So if you want to find out how many degrees or radians this is, you would just do inverse cosine of negative 3/7, and I'll give you the alpha value. You can do that for all of these as well to figure these out. We are moving on to projections, and this is a consequence of our dot product. I mentioned that a little bit earlier. The dot product is a projection. So if we project V onto W, that's known as this projection sub W of V. It's going to be this right here. Actually, I have a bit of a typo. This should be a squared right here. Okay. Hopefully your notes are correct. So this is a projection. This is what it means, actually. So we're going to take this V vector right here. We're going to take that length of it, and we're going to have it point towards W. So blue right here is my W vector. That's the direction. I don't care about the length of it because I'm going to take the red and I'm going to put that length onto that W, which is going to make this green vector right here, which is the projection. So that's all I'm doing is I'm projecting it onto the W. So let's go ahead and find the vector projection of V and W. So the first thing I'm going to do here is I'm going to do V dot W, which is going to be 2 minus 1 plus 1, so it's just 2. And then, oh, I put the square in the wrong part. Length squared here is going to be really just W dot W, which is 1 plus 1 plus 1, which is going to be 3. So our projection here V onto W is going to equal 2/3 of whatever W is, which is going to be 2/3 of 1, 1, 1. So this projection is going to be 2/3, 2/3, 2/3. Okay, let's get to the decomposition part. So we can decompose V, this vector V, into V sub 1 and V sub 2, where V sub 1 is parallel to W and V sub 2 is orthogonal to W. So V sub 1 is just the projection, so that one is pretty straightforward. Because V sub 1 is parallel to W, it's going to be the same thing as projection. That's exactly what we just did. But V sub 2 is going to be orthogonal, so what we're going to do is take our original V and subtract it by the projection. So we're going to take V, which is 2, negative 1, 1, and subtract it by 2/3, 2/3, 2/3. And when I do that, I'm going to end up with, so good my arithmetic is here, negative 4/3, or sorry, positive 4/3, negative 5/3, and 1/3. That's what I got. All right, and that is projections. I think we're on our last up with our dot product stuff here. Another consequence of it is computing work. Work done by a constant force, F, as its point of application moves along vector PQ, is one of the following. So work is actually going to be the magnitude of the projection of PQ onto F, or of F onto PQ rather, and then times the length of PQ, which is the same thing as F dot PQ. So F's a vector, PQ's a vector. Let's go ahead and apply it right here. A man's pushing a lawnmower handle with a force of 30 pounds. How much work is done moving the lawnmower a distance of 75 feet? The handle makes an angle of 60 degrees with the ground. So I'm going to first draw what's going on here. So we're going to take this, we're going to push this object here 75 feet. And I'm pushing down on this handle right here, which is going to make this angle right here. I'm pushing down onto this, so this force is going to go all the way to right here, which is going to be our theta equals, if it's a degree with 60 degrees, okay? This part right here is 60. And I'll do it in blue. In blue is 60. So that's 60, which means that if I were to do it all the way around here, this would actually be theta equals 300. And if you know this maybe from pre-calc or not, but this is the same thing as what would 300 degrees be? That would be 5 pi over 3. That's over 3. 5 pi over 3. Okay, so we're going to take our f here. We're going to figure out what f is. F is going to be, if you remember from one of our previous lessons, we had to use the angles and stuff like that. So we're going to have f be 30, because that's our force, is going to be, x is cosine 5 pi over 3. 30 sine of 5 pi over 3. Okay, so our force that we're doing here is going to be the angle we're pushing down on it. We're pushing down on it at 5 pi over 3, which makes sense because if you actually do this math, we're actually pushing down on the object, so that's why our force for our vertical is going to be negative here, and then our horizontal is going to be positive, and then we're going to push this along 75. So our PQ is going to be 75, 0. Okay, because there's no vertical, it's all horizontal. And so when you get here, well, actually I'll finish f real quick. So f is going to be cosine of 5 pi over 3 is going to be 1/2. So 30, so it's 15. And this one right here is going to be negative 15 root 3. Yeah, negative 15 root 3. And that's f. And then so when I do f dot PQ, I'm going to get 15, negative 15 root 3. Nope. Dot 75, 0. So it's really just 75 times 15, which I am getting 1,125, and that's actually feet pounds, because F is pounds and PQ is feet, so that's feet pounds. All right, and that's our amount of work that we're doing here, and that's going to wrap up our video here. Lots going on with dot product, so hope you enjoyed.